Hello and welcome. I am Olunlade Joshua, and this is the third part of the fluid mechanics tutorial series. Today we are going to be considering the rate of change of momentum. And the textbook I use, I found an old textbook. Let me just tell you the name of the textbook I'm using. Solution of Problems in Fluid Mechanics, Part 1. A problem-based textbook by J.F. Douglas. You can use any textbook that is convenient to you. Just any textbook that explains it well and that will make you to understand properly. Now, rate of change of momentum. In this textbook I found a wonderful explanation for this, and it is formed in the form of a question. A fluid is flowing in a tapering pipe as in the figure below. At section AB of cross section A and velocity v1, and at section CD at the corresponding values a2 and v2, derive an expression for the rate of change of momentum of the fluid between the two sections. So according to this question, a fluid is flowing, that is, starts out within these confines, and then it moves until it becomes within these confines, A prime, C prime, that kind of thing. And now we have to find or derive an expression for the rate of change of momentum. Now, as I said, I won't just state things without a backing. I want to explain and make you understand. So I'll be taking this step by step. We have to find the change or rate of change of momentum to derive an expression for this. So before I continue, let me say this. Suppose that in a small time interval t, the fluid contained between AB and CD moves to A prime, B prime. That is, let me try to redraw the diagram we had in the former slide. So here we have A, B, and here we have A prime, B prime, and then here we have C, D, and here we have C prime, D prime. So now suppose in a time interval t, the fluid in the section A so in that section AB, CD has moved to the section A prime, B prime, C prime, D prime in a small time t. The change of momentum of the fluid in the time, that is the change of momentum of the fluid, will be equal to basically the momentum of the fluid C prime D prime D. Okay, let me write it down so that it does not get confusing. Momentum of fluid C prime D prime D minus momentum of fluid A prime B prime B. That is the momentum of the fluid here. You can see we are making the red dots, minus the momentum of the fluid here. in that section. So the concept behind this naming C prime D is from C to C prime to D prime to D, basically that section, and then from A to A prime to B prime to B, that section. So once we can get the momentum here and subtract from it the momentum here, we have our change of momentum of the fluid. So now how do we get the momentum of the fluid at C prime D? Let me get a new slide. Okay, now let us say that, let me draw that diagram again, and we have something like this where this is A prime B prime C D C prime D prime. So suppose we have this, we know the velocity at which point A is moving, or the velocity at this side of the fluid, which is v1, and we know the velocity at this side, which is v2. So we can safely say that if we want to get the distance d1 and the distance d2, remember velocity is the time rate of change, or the rate of change of displacement or distance. So now d1, we can easily say that d1 is equal to v1t and d2 is equal to v2t. I hope this is clear, where this t is the time it takes. Since it takes the same time, so this and this are the same, still t. So the distance cc, that is from here to here, which is d2, will be equal to v2t. And now we can safely find the mass of the fluid. Recall, what we want to get is the momentum, and we know that momentum is equal to the mass times velocity. So now we need the mass of this fluid in point cc, considering the mass of the fluid c prime d, which will now be equal to, well, okay, let's use this. Recall that density is equal to mass over volume. This is capital V. Please don't confuse it with velocity. Recall that rho, density, is equal to mass over volume. Now mass will be equal to what? Mass will be equal to rho V. That's rho times volume. I'm writing it in full because I do not want you to confuse it. And we know that our discharge Q is equal to what? V over T. That's volume over time. So easily we can say that mass will now be equal to, because volume will be equal to QT, will now be equal to QT. And we know that Q is equal to A times velocity, which is V. So we can simply say M is equal to A, which is area, times velocity times time. So the mass of the fluid here will be equal to the area. Let's represent that with A2, the area at that cross section, A2, multiplied by the velocity, V2, multiplied by the time, T. Oh, sorry, I left something out. Rho, density, multiplied by the density, rho. So this can also be written as rho A2 V2 t. Now recall that the distance is v2 t2. So just put that in mind for now. So you can see how all this is getting related. And similarly, the mass of fluid at a prime, b prime, b will be equal to rho a1 v1 t. And what is momentum? Momentum is mv. Is that correct? So now we can easily say that momentum of fluid c prime d prime d will now be equal to this mass, which is this rho a2 v2 t multiplied by velocity at that point, which is also v2. So this will be equal to, I'm going to erase some things here now to clear up some space. Okay, this will now be equal to rho a2 v2 square t. And similarly, momentum of fluid a prime b prime b will be equal to rho a1 v1 t multiplied by v1, which will now be equal to rho a1 v1 square t. Okay, but we are still not done. What we want to find is the change of momentum, which will now give us the rate of change of momentum when we divide it by time. So now what is the change of momentum? This is another slide. The change of momentum of fluid between AB and CD in time t will just be equal to PA2 V2 square t, which is the momentum of fluid C prime D minus rho A1 V1 square t, which is the momentum of fluid A prime B. And you see that this is simple. So now the rate of change of all that will now be equal to, it will just be divided by time. Rate of change of momentum will be momentum divided by time. So that is rho a2 v2 square t minus rho a1 v1 square t all over time. And easily this will become rho a2 v2 square minus rho a1 v1 square. And we can collect like terms, or we can factorize a2 v2 square minus a1 v1 square. And we've gotten our equation, or an equation, for the rate of change of momentum of fluid. But we can simplify this further. We know that for continuity of flow, the section we had was something like this. We know that for continuity of flow, Q1 must be equal to Q2. Q must be equal to A1 V1, which is equal to A2 V2. So easily we can substitute something here. So that rate of change of momentum will be equal to rho q v2 minus q v1, which simply is rho q v2 minus v1. We can still simplify this further, and let me get a clean slide. So rate of change of fluid between AB and CD will be equal to PQ V2 minus V1, as we got in the equation before. And we can recall that density rho is equal to W over G. Rho is equal to W over G. This is from basic physics. So we can just substitute that WQ over G V2 minus V1. And this is our equation for the rate of change of momentum of fluid between AB and CD. If what I did looks like magic, it's not. Please, you can go over it and over it again until you understand it. It is actually quite simple. Basically, the rate of change of momentum of fluid between AB and CD is mass per second flowing multiplied by the change of velocity. Please go over it and over it again until you understand it. Read the textbook, do further research, make sure you understand it, and then go on to the next video. The next video is on energy of a flowing liquid. It is very important, and I will see you then. Don't forget to subscribe to this channel and like this video, and let me know what you think in the comments below. Thank you. I am still Olunlade Joshua, and I will see you in the next video.